So every problem with forces, we're going to be acting the same way. First, we're going to have to draw a free body diagram. And find what is the net force. This is the goal. What is the net force? And the force is a vector, so it's going to have a horizontal and a vertical component. And then I'm going to have to take my vector, and this is going to be f sub x, and this is f sub y. And I'm going to use SOHCAHTOA to split between horizontal and vertical components. It's exactly the same as kinematics in two dimensions. Once I have that, of course, I'm going to be able to use the equation, and I'm going to have an equation that says that the force in the x component is mass times the acceleration in the x, and another force that says that the force, the net force, and of course this is always the net force, it's equal to the mass times the acceleration in the y component. And once I have this, because this is horizontal and this is vertical, if the problem requires so, then I would use kinematics, right? And I would use the same kinematics to solve them. And so they can ask, I have an object of this given mass, how fast or what is it going to be 1 second down the line? So there's very little information, right? They are just telling us it's 1 second down the line, there is the mass of the object, and I'm applying these forces. And that sounds like it's not enough, but it is. Because first you're going to draw the diagram, figure out what are the forces acting, calculating the net force, which is the sum of all the forces, taking that vector and splitting into horizontal and vertical components, and then from that we're going to be able to write the equation, Newton's second law, solve for the acceleration, and once I have the acceleration, in fact, I'm going to always have initial position, I'm going to have the initial velocity, and I'm going to have now the acceleration, so I'm going to have this one, I'm going to have this one, and I'm going to be asked about either one of those. What's the final position, what's the final velocity, or what's the time, and usually even another one. For instance, how long does it take to stop? Then you know that the velocity is 0, so you can find the time because you're going to have this one, you're going to have this one and this one. These are not 0, this is whatever number, right? And then I'm going to have this one or this one, and then I can find this one missing this one. So I have then 4 missing 1, ask for 1. So you'll see it's always the same time. So that's why it's important to understand kinematics. And again, this is kinematics in 1 dimension, so the motion becomes trivial. If this is kinematics in 2 dimensions, because in fact there is net, horizontal, and vertical, do not forget you split it in 2, and then you use the time is the parameter that connects vertical and right. Time is the parameter that connects the same event. Time is shared by this phenomena. So we can take first diagram, free body diagram, find the net force, which is the total force, add all the forces together. This is going to be a vector, then use SOHCAHTOA, split into horizontal and vertical, take the horizontal, find acceleration horizontal, take the vertical, find acceleration vertical, and use your kinematic equations to solve any question that they're asking you in that particular problem. So chapter 4 is about forces in action, we say. We're going to use the concepts that we developed in chapter 3 about the Newton's law and seeing how they act and what exactly a force is. And then we're going to use chapter 2 and chapter 1 then to, once we have the acceleration, derive the equations of motion for an object. Now, in the case of forces acting on objects, we're going to distinguish in this course about 5 different types. We're going to see weight, we're going to see tension, we're going to see normal, we're going to see elastic force, and then we're going to see friction force, which always opposes, and this is from a phenomenological perspective, so to speak. Why? Because we call forces following Newton, whatever we have, if you remember second Newton's law, that's going to be the force is equal to mass times acceleration. So anytime we know that we have an acceleration that is non-zero, right, it is because there is a change in velocity that is non-zero. In other words, there's a change in velocity, which of course could be because of the magnitude, or it could be because of the direction change. We know that. Now, the problem is, of course, how does this work? You could say that the force is defined as that interaction that produces an acceleration, which means there is a change in velocity either because of magnitude or direction. Or you could go the other way and say, well, we observe that some objects are changing their velocity and we calculate how fast they're changing their velocity, which is what we define as an acceleration. With second law of Newton, we know that that acceleration multiplied times the inertia of the object that we define as the mass, it's equal to a quantity that we call a force. And forces intuitively are pushes and pulls, but we have to go beyond that concept and just saying that a force is present whenever a net force is present whenever there is a change in the state of motion. And that's basically the definition. So every time that we're analyzing an object moving in space and we see the object is changing its velocity, it's going to have an acceleration, and that's produced because of a force. Then we're going to try to find what is the source of this force. And as we say, we're going to analyze 4 types of forces. It's going to be weight, is going to be also that we call F sub W. We're going to have the normal force. We're going to call F sub N. We're going to have tension. F, let's call it F sub T. We're going to have the elastic force, sometimes called Hooke's law because the equation called Hooke's law because of Hooke, Robert Hooke, the English physicist who introduced it. And finally, we're going to have friction. Now, from all these forces, again, these are phenomenological explanations. All of these forces might be acting in, which we can call F sub F. Now, from all of these forces, we know that the weight is the minus mass times g. Why? Because it's always pointing downwards. So that's, we can keep the negative here or call it positive and then replace g with minus 10 or minus 9.8 or whatever you want. Normal and tension forces do not have an equation. They need to be derived according to the scenario that we're analyzing. The elastic force is always taking the form of a k, which k being a constant of elasticity, times the change in displacement. Or the change in position, which again, if you take a spring, the spring is at the zero position. We can call this the stationary position. So the spring is just the natural state, and then you can either compress it, and then you're going to have final position. Therefore, delta x is going to be x minus x sub 0, and of course this is negative. So remember, that's a kind of a vector. So the force, elastic force, is going to be acting against this object. Or we're going to be able to define the opposite case where we have the spring stretched. And so we're going to have a final position here, right? And so the delta x is going to be, of course, x minus x sub 0, which is going to be, in this case, positive. Now, that means that I'm having a negative displacement, a positive displacement. What sort of restoration force do I find? Well, elastic force. Elastic force is opposite to the displacement. So the elastic force is going to try to recover. That's going to be the elastic force, and that's going to be the elastic force pointing in the opposite direction. It's going to try to recover the stationary or the equilibrium position. In a first approximation, elastic forces apply pretty much to every material. You could actually see that if you plot a force versus a strain, how much an object actually extends or stretches elastically, you can see that pretty much it looks something like this. We could plot here, let's say, the amount of force that you apply, and then here, let's say pulling, for instance. Pulling, it's much more obvious to see that's going to be the force, and in the vertical axis we can see how much is the displacement. Now, if something happens, this is of course a line, because this is proportional, directly proportional with a constant, which is going to be the slope. But what's important here is if you map this, you're going to see that that works like this. So every time that you increment a little bit the force, you increment a little bit the displacement. And if you release the object because of the, if this was pulling, let's say, when I release the object, I'm pulling, I'm going farther away from the equilibrium position. There's going to be a restorative force trying to go back, which is the elastic force. And once it goes back, it goes back to the original state. But at some point, if you pull too much, then you're going to see this displacement doesn't go any farther, like linearly, and it starts to kind of saturate. And at some point, it actually breaks. So this is the breaking point. So we can see that this is not anymore a straight line like this one. This is what we call the elastic regime. Forces, once you release the object goes back to its initial condition. This is called the plastic regime. In this case, you have a spring, let's say, you stretch it, and it doesn't go back all the way. It just kind of goes, it gets deformed. And that's the plastic. It's like, imagine you plastic, you take it, you can stretch it, it's flexible, it doesn't break, but it doesn't recover. And spring, actually, if you go in the elastic regime, it does recover fully, right? And so this is the elastic regime, this is the plastic regime, and then that's called inelastic, which is another way of saying it breaks. So if I apply a force, as I increase the force can be restored, but at some point it's too much force and the object gets deformed definitely. That's the plastic regime. Eventually, if I keep pulling, it's going to break, and that's the breaking point that corresponds to the inelastic regime. That's just in a first approximation, we can explain that every single material on Earth sort of follows this relationship. How much is the force that an object actually sustains in this elastic regime is going to depend, right? It's not going to be the same as spring or a rubber, that is going to be like a concrete or some other material, right? The regime in which these things, how much force needs to be, before it passes from elastic to plastic or plastic to inelastic, which is breaking point, is going to change with the material. And then we have the friction force. And the friction force, as we know, there's two types of friction. The first type of friction is kinetic friction, static friction, and the other one is kinetic. In the name, it kind of tells you. If it's a static friction, that means that it's a friction that appears when the object is static, which means stationary, is not moving. And if you have kinetic friction, that's the friction that applies when the object is actually moving. What's important in here is that the static friction always matches the force that it's applying of the object. Let's see this with a little bit more of detail, because it bears to explicit this with a little bit more of care. So let's analyze some problems from the discussions. This is in the absence of friction. We can first practice with the absence of friction, which is just simpler, and then we introduce friction. And we analyze what's the difference. So in this case, let's analyze problem 1. It says that the friend has given you a special gift, and as always, start drawing a diagram. There is a box, and the box has a mass of 10 kilograms, and it's a mystery with a surprise inside. The box is resting on a smooth, frictionless horizontal surface on the table. Unless they mention explicitly that there is friction, you typically disregard friction. Of course, if they're asking you about the friction, then you can assume there is friction. But in the exam and all that, it will be explicit whether there is friction or not, right? And then it says determine the weight of the box and the normal force exerted on it by the table. So let's go step by step. First, we're asking about what's the weight. What's the formula for the weight? Is mass times g. If this is Earth, we can take g to be 10. And so what's going to be the weight? It's going to be negative, and then 10. Mass is 10 times 10, that's going to be 100 kilograms meters square second, or directly 100 newtons. So the answer to the question is what's the weight is minus 100 newtons. Why does it mean minus 100? Because there's going to be negative force. So that's the weight. The weight is pointing downwards. What about other forces? Well, this is the idea of normal force. This is the second question. What's the normal force? Right? The normal force exerted by the table. Again, the object, if I just forget about forces now, what we saw in kinematics. If I have an object and I let it go, from a roof for instance, what do I see? I see that the object accelerates and accelerates with g downwards. So the object doesn't remain there. Why is that? We said, well, this is because of the Earth is pulling from the object, and it's pulling actually, now we know with what force. Well, that force is weight, right? The force that, that the object experiences as a result of the Earth pulling it through, because it's in its gravitational field, that's going to be weight, which in this case is 100 newtons. Now compare that situation where I just let go the object and the object falls, and I know that because the object was stationary, and a moment later it's not going to be stationary, and because it has changed velocity, then I know it has an acceleration, and because there is an acceleration, that's what I call a force. And I have identified that force as the weight force. That's how it works. Now compare that scenario with the scenario where I just let go the box, and the box is on a table. And I say, well, what force is acting here? Well, weight. Why weight? Because weight is intrinsic of the object, because it's in the presence of Earth. If I put the object on the table, the object is still itself, therefore the mass is still itself, 10 kilograms, but also the weight is acting anyways, because even if there's a table, there's still the Earth, right? So it's not that I'm just taking the table in outer space where there's no, or we can take that there's no gravitation. It's that I am in the same scenario, but now there is a table underneath. And so I observe that at a certain initial time, velocity is 0, and a final time, velocity is 0. Therefore, the change in velocity is 0, which means that the acceleration is 0, which means that the force is 0. But if I make a diagram, free body diagram of that object, I'm going to see that the object still has a weight, which is mg. But I'm saying that the net force is 0, so there needs to be another force, and that force needs to be opposing the weight, so as to the net force is actually 0, because I need to have 0 force. If there is no 0 force, the object is going to fall, but the object is not falling, it's stationary. This is what I observed. Well, I call this force the normal force, and that force is the result of the object, of the table, right? That's the table pushing the object upwards. Why? Because otherwise the object will pass through the table. And so that force that the surfaces apply on other objects in contact when they're pushing against them is what we call normal force. And again, why normal? Because it's pointing normal, perpendicular to the interface between the object and the table. This is a phenomenological explanation of why the object is not falling in the presence of a table. We just don't come up and deduce, we come up and deduce normal force from the phenomena that we observe, that when the object is let go, it just goes, but if we let it go on a table, it doesn't go anywhere. So there needs to be a net force equal to 0 because there's no acceleration, there's no change in velocity, right? Or there's no velocity, therefore there's no acceleration, there cannot be a net force. And so I can just draw the diagram, and now I can say that the net force, of course, is going to be the sum of all the forces, which in this case I have the normal force pointing upwards, and then I have the weight pointing downwards. Now be careful with the sign. If you actually draw the arrow, it would make sense not to put the, you can choose whether you want to add the sign or not. At the end of the day, just don't forget that this is negative, and there's going to be the weight, and then we just don't write the negative here because it's going to be negative, negative, positive. So understand what you're saying. Otherwise, you keep the positive, if you like, and then you see normal force plus minus mg. And of course, that's equal to 100 newtons. So what's the net force? Well, the net force is going to be 0. Why 0? Because this is what I observe. And therefore, I know that the Fn minus 100 newtons, it's equal to 0. Therefore, the normal force, of course, is 100 newtons. So that's the answer that we were looking for. Now, doesn't it make sense? Well, let's again analyze the diagram. We have a force pointing downwards, which is weight, and because it's not following the object, we know there needs to be a normal force. We point the normal force. We know, again, from the situation that the object is not falling because we don't experience the object going through the table. So the given information is the object is not going through the table. Therefore, we know there needs to apply this normal force. Now, it's important to remember that the normal force acts always perpendicular to the surface. We will see later examples where we have an inclined plane, and then we'll see that the weight does act vertically, but the normal force is acting at an angle. So not always normal force is equal to weight, not always. It's always equal to the component of the weight and any other forces acting, for that matter, in the direction perpendicular to the interface. If your interface is flat, then the direction is just simply y. But if the interface is tilted, normal force is going to be acting like this, but weight is going to be acting still like this because the Earth is here, right? So it points towards the Earth. So important thing to distinguish, we'll see this in more examples. For the time being, let's understand there's no motion in the vertical component, there's no change in motion, in the vertical component, that means acceleration is 0, which means that the net force in the vertical component must be 0. How do we justify that? Because there is a force, that's what we call the new normal force, which is perpendicular to the interface. Let's see the next part. Now the second question is they are telling us that your friend then pushes down on the box with a force of 40 newtons downwards. Let's put the box, and we're pushing with 40 newtons downwards. And they're asking us what's the normal force exerted on the box by the table. So again, let's make the free body diagram. Let's take the simple box, we remove everything else, there is no table, there's nothing. And then what do we observe? Because the object has a mass as on Earth, it's going to have weight. Because there's an interface, there's going to be a normal force. This we don't know, this we know that it's mg. And because they're telling us there is a force acting by my friend, there's another force, and that's pushing downwards, and that's 40 newtons. So what are the total forces? Well, I have to add all the forces together to find the net force. When I just don't write anything that means net, just to relax notation, and then I'm going to see, well, it's going to be the normal force pointing up minus the force of my friend, let's call this friend, minus mg or minus Fw, which is weight. And so I can replace, I don't know how much is normal, I do know what's the force of my friend, they give me that, 40 newtons, I do know what's the weight, which was 100 newtons, and so the question is how much is the normal force? Now this is the total force, right? And then I ask myself the same question. This balance of forces, according to Newton's second law, needs to be mass times acceleration. How much is the acceleration? Is this object, go back to the physical situation and ask yourself, is the object going upwards? Well, that certainly would be weird, right? We don't expect the object going upwards. Is the object going downwards? No, it doesn't go through the table. There is a table in there, and that table doesn't really allow the object to go through. So the initial velocity is 0, the final velocity is 0. There is no change in velocity. Because there is no change in velocity, acceleration is 0. So how much is this acceleration in this physical scenario? That's 0. So this is 0. So how much is the normal force? Well, normal force is going to be minus 140 newtons equal to 0. And so the normal force in this scenario is 140 newtons. Again, realize that we go step by step, be organized, and understand that every time you go back to your physical situation and see if it makes sense or not. In this case, we have to add all the negative force, all the positives, subtract one from the other, and say that's equal to mass acceleration. If the problem was telling us this object is moving upwards with the table, for instance, that we could consider this acceleration something else, but that will be given by the problem, right? You'll see that in the case of the elevator. But if they don't say anything like that, then this is what it is. Then we analyze what's the physical scenario. Well, it's not moving because it's sitting on the table. So then this is the normal force. And as you can see, the normal force now is different from the normal force before. And we already start to see something, right? By the way, this is 100 newtons, excuse me. Here's the normal force. So 140 and 100 newtons. So there's more normal force. Why? Because now the table is not just simply avoiding the box going through because of its own weight, but also it's your friend who's pushing for whatever reason. He's pushing down with 40 newtons. So the table needs to avoid the object to go down, but now just not simply compensating for 100 newtons of its weight, but 100 newtons and 40 newtons from your friend pressing. And then the question is, and what happens if instead of my friend pressing was actually pulling, right? And that's actually what they're asking in part C. And then we see, if there's more force than simply weight, we see normal force increases. Normal force is always opposing. If by any chance I release some of the force because I'm pushing upwards, what I'm going to be expecting? If 100 is with equal forces, when I push down is 140, then I'm going to expect the force to be less. Why? Because now the table is going to have to be preventing less of a force going through the table. Let's see it explicitly for part C. Now on part C, they're telling us that the box is on the table, but my friend is with the string pulling upwards, right? And it's pulling upwards with 40 newtons. So as usual, let's do the free body diagram. Free body diagram because we're only considering the object of which, for which we're describing the motion. That object is the box. And now we know what's acting on the box. Well, I have a weight force, because we have a box on Earth, mg. Then we have what else? Well, there is your friend pulling upwards, right? So that's, and if that's a string, we're going to call that the tension force. And they're actually telling us that that tension is 40 newtons. Okay, what else is in there? Well, there are two surfaces in contact, so the table is going to be pushing upwards on the box. And that potentially, that force is going to be normal force, right? So let's make the balance of forces. Well, the total force is going to be the sum of all the forces, which in this case is going to be normal force pointing up. Now tension, is it pointing up or down? It's pointing up, so I'm going to have to add it. And now weight, is it pointing up or down? It's down. And then I can replace it. What's the normal force? I don't know. What's the tension? They told me it's 40 newtons. What's the weight? Is going to be 100 newtons. So how much is that? That's going to be Fn minus 60. But let's go here, 1 second. This is equal to what? This is equal to mass times acceleration. Now, is the box accelerating upwards? No. So if I wait a second, even if my friend is pulling, what's the velocity? 0, or time later 0. It's not changing velocity. Because it's not changing velocity, acceleration is 0, and therefore this is going to be 0. So it means that this is 0, right? This is 0, which means that this is 0, which means that this is 0, and therefore I can solve for the normal force. Now the normal force is 60 newtons. That as I expected makes sense. This is normal force. It's 60 newtons. Why? When I was letting the object go, it's just compensating for weight, which is 100 newtons. If I push down, it's compensating for weight plus my pushing down. But if I pull out, it's compensating for weight minus whatever I'm helping the table to avoid the weight. Because the effective weight, so to speak, that the table experiences is not anymore the weight of the object, it's the weight of the object minus whatever my friend is pulling, right? My friend is kind of helping the table. Curiosity here, or interesting concept here, according to action-reaction. Why does the object observes a normal force, which is here, right? Which is the result, of course, of the force acting downwards. That force can be weight plus something or weight minus something. It's just the net force pointing downwards. But if you see this is, let's say, the action, which is stable on the object. But we could analyze them, excuse me, the motion of the board of the table, right, where it's sitting. And in this case, we're going to see that the normal force needs to act normal to the interface. The interface is here. That will be like the box will be here, right? So where's the normal force acting on the table? The normal force acting on the table is downwards, right? This is this will be the reaction. So what the table does on the box does on the table. Action, reaction. The reaction of the box is not on the box itself. That wouldn't be a reaction. That would be an internal force. That's pretty silly. So again, two distinct situations. And now we can even understand why if I put something very heavy, this is going to break. Why? Because that force is pushing downwards. It's trying to accelerate materials here. What's keeping materials there is just the materials, let's say, like the fibers of the wood or whatever that is. It's just keeping them together. If the fibers have a maximum tension, right? If I put too much tension, the tension breaks. That means the table breaks. Why does the table break? Not because of the weight of the object, obviously, ultimately, yes, but because I'm applying a normal force, because the object is pushing downwards on the table. So this is action-reaction in this particular case. In any case, what matters is this. Let's make a final comment in this, which is actually part D, what would happen if my friend keeps pulling up every time with more and more and more force? We can see it directly here. At the end of the day, what if this tension is equal to the weight, right? We're going to see that, but we start to see it. If this tension is larger than the weight, this is going to become positive. Now, if it becomes positive, okay, that's not going to be any more pulling down. So that means that the object is not going to be going down, which means that the object is not pushing anymore on the table. If there's no pushing on the table, then there's no normal force. So normal force is going to be extinguished as soon as we have that the balance of forces in the vertical direction are 0 or positive. Why? Because they're positive already, the object is going to accelerate upwards, and so they're not going to be anymore in contact. You only have normal force when there is contact, and if there is no contact, then there's no force. And contact means not just simply being one side with the other one, but actually one pushing against the other. Let's see this mathematically on part D. So in part C, they're telling us that there's someone pushing from the box with a force equal or larger than the weight, right? So we can draw the situation, we have the box, and there's going to be someone pulling up with a force which is larger than weight, and of course the object is going to have weight. So as usual, the first thing we do is just make our free body diagram. We're analyzing the box, and we're going to put the tension up because it's pulling upwards, and then we're going to have a weight. And now the question is going to be any, again, careful with the sign, I'm not being consistent, but of course, you can just keep it positive if you wish, and just add it manually, right? You could say that this is the modulus, and then you keep it positive, or you could say that this is a vector, and then write this, whichever way you like, right? But then you don't say force tension minus force weight, you would say force tension plus force weight, right? So whatever you do, just be consistent and don't make, understand where things pointing. And now the question is, anyways, what's happening with the normal force, right? What happens with the normal force in this scenario? Okay, this scenario, remember, what's the normal force? It's the reaction force of two surfaces in contact with each other. One surface pushes the other, right? And again, action, reaction. One object pushes the other pushes the one, right? What A does to B, B does to A. What A, which would be the table, does to B, let's actually draw the table here like this, right? So what the table does on the box does on the table. With a difference, this and this are opposite, so they're minus, right? They're the same magnitude but opposite direction. And this is what we observe here, action and reaction, right? The reaction of the normal force is not the reaction of the weight, right? Reaction is what A does to B, B does to A. So the reaction of the weight is not the normal force. Because there's a weight, there's push. Because there's a weight, no. Because there's a weight, and that weight is not counterbalanced in any other form, then we're going to have a normal force that compensates for that. But what happens when the normal force, I'm going to put the balance of forces. I could even just say, let's make the balance of forces here. We will say, what's the net force? Well, the net force is going to be, again, we can just get rid of that, and then just is the sum of the forces. And what forces do I have? I have a tension, and then I'm going to have also a weight, right? And then I'm going to have that this is at least 100 newtons, and this is 100, newtons, and this is at least 100 newtons. And of course, this is mass times acceleration in the vertical component, right? So now I ask you, is there any way normal is going to be pushing? If there is any normal, it's going to be pushing upwards, right? But we put this in parentheses because we don't know. Is there any normal? Let's analyze this scenario without considering normal yet, just like something that we have, like a lifeline, something like that, right? So what's happening here? Well, I have a tension and I have a weight. The tension is larger than the weight, so I know this is going to be larger than 0 or equal to 0. Larger or equal to 0, which means that mass times acceleration is larger or equal to 0, which means that the acceleration is going to be larger or equal to 0. Because there is acceleration, right? And I can just come quickly here. I do my entire monologue, right? Because acceleration is different from 0, then the change in velocity is going to be different from 0, which means that the final velocity minus initial velocity, or v2 if you want, or even just v minus v0 is larger than 0, which means that v is going to be larger than v sub 0. So if v sub 0 is 0, it doesn't matter, but v is going to go upwards. The object is going to start moving upwards. An instant after this starts, there's no more contact between the surface of the table and the box. So there's no normal. There's only normal whenever there is a net force acting against. Because again, the idea of the normal is the idea of the normal force is the force that you apply to compensate for the trying of one object pushing through the other, right? We can say the box tries to push through the table, and so the table defends itself by pushing upwards on the box. Or we can say the table tries to push itself, right, onto the box, and the box defends itself pushing down the table. Because we are making the analysis from the point of view of the box, and then we say because there's weight, it's pushing on the table. But that's because we're taking the frame of reference of the table, right? But if you take the frame of reference on the box, then you're not moving down. It's the table that's kind of moving up, right? And that is the result of why we have a normal force. So again, important. We have that distinction. We have to analyze things from once we wrote the diagram. Even if this kind of goes against our intuition, we have to get rid of that intuition. It's very limited because we live in a world where friction is always present. We're not considering friction here and drag and this and that, right? So, excuse me, important from here. There is a force of the table is defending itself, applying a normal force on the box, and the box is defending itself against the attempt of the table to go upwards, right? Because if I say there is a net force of the object going upwards, in this particular case that we're analyzing, right, when the tension is larger, I know that the object is going to start going up. And when it goes up, it means there is no more contact, so normal is going to go to 0. So you could even imagine that you go from 0 tension all the way to 10, 20, 30, 40, 100, and at that point, normal goes to 0. If I make the equal, that means that the normal goes to 0, and then at that point, there's no more contact. So this idea here in the box is moving upwards. But that's from the point of view of reference, and that's why relativity was going to help you understanding more profoundly these ideas. That's from the point of view of the table. So I have a frame of reference on the table. But what about from the frame of reference of the box? Well, remember that the motion of the box on the frame of reference of the table, it's equal to the velocity of the table in the frame of reference of the box. So from the point of view of the table, the box is moving upwards. From the point of view of the box, the table is moving downwards, right? Well, in this case, if the box is moving upwards with respect to the table, exactly, the table is moving downwards. And in that case, then we're going to see that the table is going to be pulling away from the box, and so this normal force is also going to 0 because it stops existing, right? So this is just to see how it actually makes sense, how everything is coherent. Everything needs to be coherent because otherwise physics will be just a waste of time, right? But the theories are coherent, and they make more sense the more profoundly we just delve into the concepts, what they mean. And don't forget that mathematics they're used to find out actual numbers and make quantitative assessments, but at the end of the day we have to start from the observation of the real world. And in the observation of the real world we see we're just pulling, and at some point we're producing more force than the weight, and so there's going to be a net force going up, and then there's not going to be more contact. Therefore there cannot be normal force because we introduce normal force as the result of saying, oh, the object doesn't keep going, doesn't go through this other object. But now we don't need to justify why the object doesn't go, why the box doesn't go through the table, because the box is moving upwards. It does, of course, it doesn't go through the table. It doesn't try to go through the table. It's just in the presence of weight and nothing else that we say, hey, this is trying to go through the table, but it's not. I need to somehow justify that it's not. How do I justify that it's not? Because there's a normal force. But now I don't have to justify that it's not going through, because of course they're not going through, they're going in opposite directions. So that's just the understanding of the normal force. Something similar you could see in tension. And you have an object with a certain weight, right? Let's say that you have an object hanging, right? And a friend starts pushing. There's going to be a weight of the box, and there's going to be the tension going up, and there's going to be a friend, let's say, pushing up. And so I ask, how much is the tension? Well, if you're hanging an object, just grab an object, right? A bucket or something, even if you like water, right? And then you feel like the weight. How are you compensating with the weight? With the tension, let's say, of your arms, compensating for the weight so the object doesn't move. There's no change in velocity, which means there's zero acceleration, there's no net force. But if a friend starts pushing upwards, what do you feel? You feel that you need less and less and less force to actually hold the object. If your friend just goes crazily up, you just don't have to do anything anymore. You just disappear. The object keeps going up without you. So that's kind of like, say, the equivalent, but for tension on this scenario that we have seen with normal force. Let's see more problems. So problem 2 in discussion is a very interesting example where we're having a situation where there's not anymore like a balance, where things are moving, which kind of goes back to the problem which is problem number 1. In this case, there's a woman on the elevator, and the elevator, the problem says, is accelerates downwards with an acceleration of minus 0.2 g, g being, of course, 10 meters per square second. The question is, what's the weight, and then what is the weight that the scale reads? So let's start answering what's the weight for the woman. So the woman, of course, what is the weight? Weight is defined as I have an object on Earth. This is going to represent now the woman. And then I say that this object, because it has a mass, experiences a force equal to mg downwards produced by the Earth. And again, action-reaction, the Earth does onto the woman what the woman does onto the Earth, right? So here, Earth is pulling from the woman. The fact that the woman is in an elevator, on top of scale, or even if she was riding a bike, or whatever condition you want to say, it's irrelevant, because weight is the result of gravity pulling from the woman. So the weight of the woman is irrelevant, it's just given by mg. And in this case, weight, of course, is going to be 65 kilograms times times 10 meters per square second, which is, of course, 650 newtons. If you want to add the minus, so we could say minus 650 newtons, which is the weight of the woman is pointing downwards, as we saw. So the answer for the weight is, of course, minus 650 newtons, or just 650 newtons if this is the modulus. Doesn't matter. Okay. The second part of the question is, what's the scale reading? And that's a little bit more tricky. What the scale is measuring is actually the reaction of the woman pushing on the scale. So we can go now back to the story and say, well, we have a woman, and the woman is experiencing a force. What's that force? The force is the free body diagram of the woman. Right? So we have a force, and that force is weight. Do we have any other forces acting on the woman? So just take the woman and see what's acting on the woman. Well, obviously there's another force, which is the force of the elevator pushing upwards, or the scale, if you wish, pushing upwards on the woman. And so I'm going to have to posit there's another force, which is the force of the woman, the normal force. Why do I say there's a normal force? Forget about the normal force for the moment being, and say that this is a woman just on Earth. What she experiences is a weight. The fact that the woman is not falling through, it is because something is sustaining that. What's that? That's the resistance of the surface to let that woman pass through, and that is normal, which means perpendicular to the surface of contact. And that we call the normal force. And then we know also that that's going to be given the total force, the net force, right? We could just say, let's say that the net force, according to Newton's second law, is going to be the sum of all the forces, and that's mass times acceleration. So what's the net force? Well, that's going to be the normal force minus mg, which is 650 newton. And that's equal to mass times acceleration. If the elevator was stationary, acceleration would be 0. It's not accelerating the elevator, right? So the woman who is inside the elevator is not accelerating. So again, we always think about it in terms of the woman. If there was no normal force and the elevator was accelerating, the elevator would just pass through the woman, right? We don't observe that. That's kind of weird. So it's with the elevator. So the acceleration of the elevator is the acceleration of the woman. Otherwise, the woman will just fall and then they hit or something like that, right? So we have to make physical sense of the situation. So the woman has an acceleration. What is the acceleration? The acceleration of the elevator. And what's the acceleration of the elevator? Pointing downwards, 0.2 g. So this acceleration is not 0. This acceleration is, in fact, is going to be the mass times minus 0.2 g. And so we can write those things here and say force normal minus 650 newtons, it's equal, which is the total force, it's equal to the mass of the woman, which is 65 kilograms, times minus 0.2 g. This is 2, because this is minus 2, which is 0.2 times 10, that's 2, with a negative, so minus 2, and then 65. So minus 2 times 65 is minus 130. So then we're going to have force minus 650 newtons is minus 130, which means that the normal force is how much? 130 plus 650. This is negative, goes here as positive, and then eventually you find out the solution. Let's write it somewhere here. We find the solution that the normal force is actually minus 130 plus 6, it's going to be 520 newtons. And now the question is, how much is the scale measuring? So the force experienced by the woman is 520 newtons. It's not anymore 650 newtons. Why? Because of the acceleration of the elevator is imparting a normal force, which is 520 newtons. So if we want to figure out what the scale is reading, let's think how a scale reads. Why does a scale read a weight? Because you push down on the balance plate or on the scale, right? You push down. So your hand pushes the scale, the scale pushes your hand. The scale is pushing the woman, but what the scale does to woman does to scale. Action, reaction. And so in this case, how much is going to be experienced in the scale? The scale is going to experience, the scale is pushing the woman upwards. That will be this one. The scale is pushing the woman upwards. But then the second scenario is actually the woman pushing the scale downwards. Right? That's the normal of the feet of the woman pushing on the scale. This is the normal of the scale pushing on the feet of the woman. Action, reaction. And so what the scale is going to be reading is actually 520. So what is defined as weight? We say that weight is defined as m times g. And now we're saying that that needs to be equals to 520 newtons. So then what's happening now is that we just divide by 10 times 10, and so we find that this is 250 over g, which is 52 kilograms. So what the scale is going to be measuring, what the scale is going to be measuring is 52 kilograms. The scale is not going to be measuring anymore 65 kilograms, and it's going to be measuring 52 kilograms. And this is a good observation, because sometimes we confuse mass and weight, and that's just simply because every time we measure the weight, we measure it on Earth, and pretty much we can take that everywhere that we are on Earth, provided that we're close enough, acceleration is going to be g, right? So it's going to be 10, well, okay, maybe it's 9.8, 9.7, 9.6, at most 9.6, something like that. So you have to be very far away from Earth to actually start observing an acceleration that changes. So we say acceleration is constant in free fall because acceleration is approximately always the same. It does actually change, but changes so little that we can take it as constant. But this is important. If we had thought that the scale is measuring mass, the scale will be broken, because it's telling us it's 52 kilograms. And mass, remember, is a measurement, or is the definition of inertia, which is the opposition of an object to change in its state of motion. And that opposition, it's always the same because it's proper of the object. It's a thing of the nature of the object itself. The woman hasn't lost mass. She's still the same woman, and so she is 65 kilograms. But her weight, as measured by the scale, is 52 equivalent, we should say is 52 equivalent. The scale doesn't really measure mass, it measures force. And so the force, then it converts to mass, assuming that there is only a simple force, which is the woman pushing down, and no acceleration. But if we introduce acceleration, then things go down. So from here we can see an interesting thing, which is the woman going downwards. Let's make an arrow saying that the woman is going downwards there. So the acceleration is downwards. If you're going downwards, your weight is less, your apparent mass goes lower. If I increase this acceleration and go back to this equation, if instead of being 0.2, this were minus g, which is what we call free fall, this would have been minus m times g, which would have been minus 650. Minus 650, this would have passed here, instead of minus 130, would be plus 650. Minus 650 plus 650 is 0. So how much would have the balance, the scale measured? 0 newtons, and therefore would have converted 0 divided by 10, 0. So 0 kilograms. What does that mean? Well, that's actually free fall. That means that you are floating. There's no more gravity. And this is an interesting realization, because at the end of the day, falling in free fall, in the absence of friction, is going to be the same as actually being on space without gravity. And this is an important realization that triggers, so to speak, or inspired Einstein to develop his theory of general relativity, right? Saying that the gravitational fields could be just simply explained as accelerations, and there's something in there, right? Simplified, of course. But that's this idea over here. An object falling down at g will observe or will experience pretty much floating. And you will see that when there's like people on parachutes, right? There's friction of air, but if you were able to get rid of that. Contrarily, if the object was accelerating, the woman will be increasing her apparent weight. So if you want, you can try this. Usually elevators are going to be moving sort of with constant velocity, so that only happens at the beginning of the motion where you accelerate to gain the velocity. As soon as the elevator reaches the operational velocity, is going to be constant velocity, therefore acceleration is going to be 0, therefore the weight is going to be back to the real value. But if you stand on a scale on the elevator, and you can try this, and then you press the button, the scale goes boom, up, going up, which is this, let's say this is going down. So boom, down, and then the apparent weight is going to drop, and as soon as it reaches the cruise velocity of the elevator, it's going to be moving with the same weight, so the weight is going to go back to 650. But at the beginning, when it goes down, it just drops. At the end, when it stops, decelerates, acceleration pointing upwards is going to increase. So you can experience yourself this if you have an elevator at hand and you have a scale to put yourself in. So problem 4 in discussions is a problem with tension. It says there's the box that we discussed in problem 1, so there's going to be the box on the ground, and what it says is that your friend is going to be pulling. There's a story there which you don't really care about. There's a mass, which is 10 kilograms, and basically the physical situation is that the magnitude of the force exerted by the person is going to be F sub t, which that is already telling you that's tension, and that's 40 newtons, and it's happening an angle theta, which is 30 degrees over the horizontal, right? So the elevation. And we want to calculate the acceleration of the box. Now, how do we calculate the acceleration? Well, there's a formula we know for acceleration, which is the change in velocity over time, but that's not going to tell us much because we don't know what's the velocity. There's the other formula that we know, that is obviously Newton's law, which says that the force is equal to mass times acceleration. So if we find the net force acting on the the net force acting, we're going to be able to find the acceleration. Just remember that these are vectors, and so we need to the first thing we need to do is just to split that, find the free body diagram, right? So let's do the free body diagram for the box. So what forces does the box experience? Well, certainly we know there's tension, which is 40 newtons. What else do we know? If the box is on Earth, there is weight. How much is going to be that? M times G. M being 10 kilograms, this is going to be 100 newtons, right? Which is M times G. 10 times 10, 100 negative, pointing down. Is that all? Well, if this box was sitting on the table and is not falling, it means it's not moving vertically. It means there needs to be something that prevents that box to pass through the table. What's that? That's the force of two surfaces pushing against each other. That's normal force. So we need to add the normal force. And then we can add all the forces together. So let's add all the forces together. We see that the force, the net force, is going to be equal to the normal force plus the tension force plus the weight. And I'm going to keep the weight positive for a second and we'll see why. These are vectors, so let's distribute the vectors into their components. Let's maybe do it here. What do we know about the normal force? The normal force is, what is the x component of the normal force? 0. Normal force is acting purely perpendicularly. And what is the vertical component? F sub n. What about the weight? Well, the weight is going to be how much? X component of weight, 0. Y component of weight, minus 100 newtons, right? And finally, we have the tension. What is the x component of the tension? And then we have to do SOHCAHTOA, right? So the tension is like this, and this is theta. So this, if this is tension y component, and this is tension x component. So this is the adjacent to this angle, so adjacent is SOHCAH cosine. So that's going to be just simply the force of tension modulus, right, times the cosine of 30. And what's the y component? Is going to be the modulus of tension, the sine of theta again. SOHCAHTOA. So is sine equals to opposite divided by hypotenuse. This is hypotenuse. So opposite is hypotenuse times sine of theta. And so I can put that and I can replace with a number. Cosine of 30 is 0.86. So 0.86 times 40. We'll check in a second. Then this is 0.50 times 40, which is 20. So this is going to be 34.6. So now we have all 34.6, yes. So now we have all the numbers in here, and then we can add them together. So how do we add vectors? Well, we only have to add components. So let's add all the vectors together, and we find that the normal force has an x component of 0 plus 34.6. So 0 plus 0 plus 34.6. And the y component is going to be F sub n, which is the normal force, minus 100 plus 20. That's the y component. So I can rewrite that as the net force equal to 34.6 in x, and in y I'm going to have normal force minus 80 newtons. So that's the force. The question is, what's the acceleration of the box, right? So then I'm going to have to remember that force is equal to mass times acceleration, and so I can describe into x and y motion, or vertical and horizontal. This is going to say f sub x is max, there's no component of the mass in x, and this is f sub y, which is the mass, a sub y. So what we're going to find in here is that the x component is 34.6. Can we go here? 34.6. It's equal to mass times the acceleration in x, and this is going to be that. Let's write it down here. So let's put it here. We have more space. So x is going to say that 34.6 is equal to mass, which is 10 kilograms, times the acceleration in x, and the y says that the force, which is force normal minus 80 newtons, it's equal to 10 times a sub y. Okay, important thing here. How much is a sub y? I cannot solve for a sub y until I figure out f sub n, because I have two incognitas and a single equation, right? So here is where, again, mathematics needs to remember we're doing physics, and this represents physical scenarios. Of course, you could have realized this at the beginning, but let's say that you were just in automatic pilot and didn't see. How much is the acceleration in the y direction? If my friend is pulling this thing, right, and I don't think, let's make sure. Yeah. If my friend is pulling in this direction, but the box is not lifting, the box is just simply moving horizontally, what is the change in velocity in the vertical component? Initial velocity was 0, he starts pushing. Has it changed position? No. So velocity is 0. Velocity here was 0, velocity here is 0, change in velocity is 0, acceleration is 0, net force in the y direction is 0, acceleration is 0, net force is 0, and so immediately f sub n minus 80 is equal to 0, which means that f sub n is equal to 80 newtons. Okay, that was weird, 80 newtons. So that's the answer to the question. How much is the normal? The normal is not anymore 100, it's only 80. Why? Because the tension vertical component is lifting some of that weight out of the table. So the table doesn't need to push anymore to avoid the box to fall through, right? And what's the x component? Well, the x component is acceleration in x is, of course, 34.6 divided by 10, which is 3.46 meters per square second. Acceleration is y is equal to 0. So what's the total acceleration? Of course, because acceleration is just going horizontally, acceleration is 3.46. And what is the normal force? Is 80 newtons, which I think actually that's the question for, yeah, that's actually part B. So answer to A, 3.46 meters per square second. Answer to B, 80 newtons. What we see again is an example. We're having a force in diagonal. That means a two-dimensional description of the force. Let's split into horizontal and vertical, and let's analyze horizontal and vertical motion as independent things. And let's relate back to the physical situation to realize what information do we know. We don't know the normal force, but the normal force needs to be such that the object doesn't fall through when there is a net force of minus 80 newtons pulling down, pushing down, right? So how much then needs to be that force? 80 to compensate. If they were telling us that this object is going in diagonal, then they would have to tell us, well, we would know that the normal force is 0 anyways, right? Because they're not in contact anymore. So if they're in contact, means that there is no motion in this direction. Unless, of course, the table was moving with the object, as we saw in the example of the woman in the elevator. But at the end of the day, you need to understand the physical situation, observe the forces, put the forces into dimensions, split in vertical and horizontal, solve for acceleration. If we wanted to know now what position is going to be the box 3 seconds after you start pulling, we would have the acceleration. And so we would just use kinematic equations to find that distance. At this point, this program is ended, but again, we have figured out what are the accelerations. What's the reason of that acceleration? Now we know. Well, the object has a weight, we are in Earth, the table is pushing up, and my friend is just going with a string, applying a tension force at a certain angle. So problem 5 from the discussion says there's two boxes, A and B, and forces A and B, and the forces are connected by a lightweight cord and are resting on a smooth frictionless table. The boxes have a mass of 12 kilograms and 10 kilograms. And a horizontal force of 40 newtons is applied to the 10 kilograms box. So we can assume there's a force here, and that force is actually given as 40 newtons, right? And there's a string that connects these two boxes. If you wish, let's make this, okay? So the chain is just there. And this chain has tension. If the chain was folded, like no tension, then there will be no tension. But as soon as you start pulling, this is going to stretch to the point that it reaches perfectly straight, and then it's going to be pulling and there's going to be tension. Otherwise, again, there's no tension, obviously. So then we have this scenario, A and B. Now we have the force acting. And the first question is, what is the acceleration of each box? So we're going to find the first question, which is acceleration of A and acceleration of B. This is the question. This is a case of motion in one dimension, so although accelerations are vectors, we're happy just dealing with horizontal motion purely. You'll see that even though that's actually the case, in the presence of friction, there's going to be a subtlety there, because in friction, you're going to have to use the normal force. So even though you're going to be moving horizontally, the friction is the result actually of the vertical component, right? Or the friction, it depends on the vertical component. But not in this case. This is frictionless, this is free to move, and that's it. Just a curiosity, probably here it says a lightweight cord. In physics, we're going to assume that the cords, the strings, the ropes do not have any mass, and certain other assumptions that are made out about the strings, not to include them in the analysis. This is an assumption that is good for physics 2053. This is even true for most of the time for physics 2048, which is physics with calculus. Unless you're an engineer, you probably don't gain much actually putting weight into strings and this and that, right? So let's just keep it simple. Every time we see string, every time we see rope, every time we see chain, we can assume it's massless. It doesn't really play a role. It's just like an ideal body there, imparting forces or transferring forces from one point to the other, right? Okay. So then we said, what is the acceleration of each box? So, balance of forces and free body diagram. Let's do the free body diagram, right, for object A. For object A, what we observe is that there is a force acting in ways. What's that force? Well, the force of the tension. Again, free body diagram, we only take one object, isolated from the rest of the universe. Well, that's a force, and we're going to call that the tension force that experiences A. What about object B? In the universe of object B, we're going to observe what? We're going to observe that there is a force acting in that direction. What's that force? Well, that's force of 40 newtons. What else do we know? Is there any other force acting here? Well, there is. What's that? Well, there is a string attached and pulling that way, so I actually have a tension here. You see the difference, which is the tension in B. You see the difference in here? This box only has a force, which is tension pointing that. The string or the rope is pulling from the box, so it's making a force on the object. The string is pulling from the box and is making a force on this object. That's why it's important to understand that this is one object, this is another object. If I'm explaining or describing the motion for this object, isolate this object. If I'm doing it for this one, isolate this one, forget about the rest. Obviously, you have to incorporate it physically, but that's it. And why is it necessary that this is actually the case? Because what the string does to the mass A, or to the object A does to the string. So the string is actually being pulled this way, right? And the string is attached to the box, so the box is going to try to be moving in this way. And conversely, you could do the argument in there, right? So these tensions are acting on each other, right? They're actually, excuse me, they're actually the tensions acting in this problem. So if we make the analysis, the string is pulling from the box is pulling from the string, and then I have the string that is being pulled this way and attached to this mass, so the string is going to be pulling this mass that way, and this mass is going to be pulling the string this way, which is the reason why this string is pulling from this mass is happening in here. So if I take the string, I'm going to see that the string is experiencing a force here and a force here, And these forces cancel, because if they were not canceled, then I would be stretching, and I'm assuming this is not a stretching, right? So there's a force on the string which is due to a reaction force of this one, and there's a force on the string which is the result of B pulling from the for the string, which is the reaction to this one, right? Opposite direction. So this is the reaction of the string due to, let's put in parentheses B and parentheses A, meaning this is the tension on the string due to A, this is the tension on the on the string due to B, and this is of course the string. Because the mass is because these objects are massless, acceleration is just actually just net force is not going to be. So that means, of course, which is a general thing in tension, that this force needs to be actually the same as this other force. That's all discussion just to justify actually this. Now let's analyze first object. Now we have that the sum of all the forces, which is the tension. Now I can call this, by the way, force sub tension. I don't need to write A or B anymore. So now I can just the analysis of forces for this one. The total force is going to be equal to what? Tension up and nothing else, and that's mass A, acceleration of A. Let's substitute numbers. The force of the tension I don't know. The mass of A is going to be 12 kilograms. The acceleration of A is what we're trying to find in here. Yes. Let's go, capital. Let's go to the second one. How do we make the balance of forces here? The net force, which is again the sum of all the forces. What forces are acting here? Positive, 40 newtons. Negative, the tension, which is the tension of the string pulling from the box, which is the same as the force of the string pulling from that box, in just in opposite direction. Positive, negative, I see it. And then that's equal to mass of B times acceleration of B, which of course I can replace. Mass of B is 10, so that's going to be acceleration of B. So let's come over here and realize that we have the following. F of t, it's equal 12 times acceleration of A, and second equation, it's equal to, second equation is actually 40 minus ft, it's equal to 10 times A sub B. So I have 1 incognita, 2 incognitas, 3 incognitas, 2 equations. It's indeterminate. Not really. There's another piece of information that comes from understanding physics. If this box is being accelerated, if this box is stationary, it's not changing velocity, what is the acceleration? 0. Changing velocity is 0, acceleration is 0. What will be the acceleration of this box? 0. If this box was not moving, this box would not be moving. This box moves if this box moves, and if this box moves, if this box moves. So then obviously A sub A must be equal to A sub B. And so that we can call that A. This is the second assumption that we make together with the tensions. Tensions are the same, they're just applying in opposite direction. Accelerations are also the same. And they also apply in the same direction instead of the tensions they're applying. Why? Because if this was positive and this was negative, that would mean this was going this way, that would be that way. The string will stretch, and we say it's incompressible. The stretch is, the string is ideal. It doesn't stretch, and it just doesn't break. It doesn't do any fancy stuff as real strings do, so this is the truth. So AB is equal to A, and so the system becomes much simpler, because the only thing I have is that the tension is equal to 12 times A, and 40 minus Ft, it's equal to 10 times A. I can use this one and replace here, so I have 40 minus 12A equals to 10A, so I have the 40 is equal to 22A, which means that A is 40 divided by 22, which is equal to 1.82 meters per square second. And what is the tension? Once I have the acceleration, I could just go back and replace for the tension. So the tension is going to be 12 times 1.82. This is 12 times 1.82, which is going to be 18 plus 3 point, so about 21.8 newtons. So what is the tension? 21.8. What's the acceleration? 182. Again, if accelerations were different, this would be moving faster, and so the distance between the boxes will break, but we have imposed that condition from the fact that the string cannot be stretched. And that obviously means that both are moving the same way, in the same direction, in the same manner, with the same acceleration, right? This is a physical realization. Second physical realization is the string cannot go in other ways, because then we will be stretching the string, right? If there was a non-zero force in here, we would have to be moving some way. And that will be a problem, because mass is 0, And also we will be saying, which is the actual reason, is saying that the force of the tension being non-zero in the string, right, that the balance of forces on the string, not just the tension, the balance of forces of the string on the string, which is mass times acceleration. You can ignore this, but just for the sake of completeness, this is 0. So how we would expect this to be 0, but we're saying that this is non-zero. You cannot have a net force, otherwise this will be divine and the acceleration is infinite, and that doesn't make sense, right? So anyways, it's just the real reason, or the physical reason why this is consistent. Otherwise it wouldn't be consistent, right? So assuming that the mass is actually 0, lightweight core, then we have to take these assumptions. This is more important maybe from physics with calculus. For us, we're happy with just saying acceleration is the same, tension is the same always along the string. You cannot just change that, otherwise you have problems in physics. Tension being 21.8, acceleration being 1.82. And with that, I think we have answered all the questions for this problem. Let's move to another one. So let's try now problem number 7. So it says there's a block it's on a slide. The slide has 30 degrees inclination. Sorry, the slide actually has 22. Degrees. The mass of the object is 7 kilograms. Let's write here theta is 22 degrees. And with the horizontal, right, so we're elevating 22 degrees. So actually this will be 180 minus 22, which is 168, 58, excuse me, right? So 90 plus the complementary 68, so 158. Determine the acceleration of the block as it slides down. So we know it's sliding down, right? So it has certain velocity here. We're asking, or it's going to be having a velocity, but certainly what's going to have, excuse me, it's an acceleration, right? Because this is sliding down. It's telling on the wording of the problem. Determine the acceleration of the block as it slides down the plane. And if the block starts from rest 12 meters up the plane from its base, what will be the block's speed when it reaches the bottom? So this is an example of, we're going to first find the acceleration, then we're going to use kinematics to find more information. That's actually pretty beautiful, because only from this information that there is an incline, the incline has 22 degrees, and then the mass is 7 kilograms, we're going to be able to predict the position of the mass through time, right? Of course, assuming it was infinite, blah, 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 but basically, as it comes down. Okay, and the other thing is that it's 12 meters, otherwise we'll be missing information, but we'll go to that in part B. So let's go to part A, which is asking about the acceleration. How do we find acceleration? Well, based on the change in velocity, but we don't know that. How else? Through Newton, so it's a force. And force is a vector. Now we have a scenario where we're actually moving into dimensions. We're changing x position, and we're changing also y position. So we're going to have to do the classical thing of distributing. Now, reference frames that define our axis of coordinates are arbitrary choices. You can choose whichever frame of reference you like. However, there are some that are more convenient than others. In this particular case, we're interested in the motion along this slide. So one option is, of course, to define x and y as traditionally are done. So this is x, this is x and this is y, which is traditional because this is the ground. But another option might be just to take this diagram, and this is 90 degrees, just tilt it, and align it with this axis. And so we could define another diagram where this is y and where this is x. And so let's call it prime, not to confuse. So how do we go from here to here? Well, this is just basically 22 degrees rotated in this direction, and we have it. So we can describe everything in this, or we can describe everything in this. Let's use this one, and you can probably try yourself this one at home if you have any questions, ask in discussion sections or office hours. But basically the idea here is going to be it's irrelevant of the frame of reference that you use. Therefore, the motion described here or described here should be the same. The value of the acceleration should be the same. Of course, the components in x and y are going to be different than the components in x prime and y prime. But the absolute value of acceleration and the vector in space should look exactly the same thing because it's irrelevant from the axis of reference, right? So, let's take the analysis of this scenario. So, excuse me, let's take free body diagram of the mass. Now we're going to have a mass. I'm just going to make the mass to be a smaller square, right? And then I say, what are the forces acting here? Well, of course, this is on Earth, so I'm going to have weight. What else do I have? Nobody's pushing it. horizontally, vertical, or any other ways, but this object is pushing down on the ramp. So we have two surfaces in contact, one pushing against the other. As soon as we have surfaces touching each other and pushing each other, we're going to have normal force. How much is the normal force? The normal force is perpendicular to the interface. So normal force is normal, which is saying perpendicular, which is 90 degrees to 90 degrees to interface. What's the interface? The interface, between, the faces. So, how is the face? If the ramp was looking like this, the force normal should be going that way. And now I can choose this axis of reference and then decompose normal force, or I can align the axis of reference and then decompose the weight. Let's do the first option. Let's call this option B, and then this is option A. So let's do option B in our frame of reference, B. So in our frame of reference B, we're going to have, this is my axis, right, and I have weight, and I have normal. So if I define in my axis of reference the force normal in x prime, again, x prime and y prime, I'm going to see that what is the component in the x prime component of axis, or direction of the normal force? Nothing. It's just moving in the y. So this is 0, and how much is in y? Whatever that value is. So force of normal. Okay. What about the weight? Well, we have the weight, and here comes the beauty of trigonometry. How much is this? Will be the ramp. So how much is this angle? Theta. Well, that angle we've been told is 22 degrees. Now, if you have a triangle, right? I just did it the opposite way. So if you have a triangle, and I tell you this angle is 22 degrees, how much is this angle? This is a right triangle, so this is 90 plus 22, so this needs to be 90, this plus this are 90 because triangles have 180 degrees. So this is 90 minus 22, we can call this alpha, and so alpha is 90 minus 22, which is 90 minus theta, which is of 68, right, degrees. But the angle I'm interested to describe my components is this one over there. But look at this. This plus this makes a perfect right angle because this is normal to the interface, right? So this angle is actually, this is alpha, and I can call this beta, right? I can call this beta. And so I realize that this is indeed, this is indeed a normal angle. So I know that beta is 90 minus alpha. But wait a second, how much is alpha? 90 minus theta. So actually 90 minus 68, it just goes you back, it takes you back to 22 degrees. So what's this angle? 22 degrees, which is the same as the incline. So that's also another advantage of using this. Otherwise, be careful when you're decomposing normal force. If you choose this axis, you're going to be decomposing the other one. But anyway, you can figure out the angle. So once we know that, then we can decompose the force into the x and y. And so I have this force, this is my axis, right? And now this is my force, and I have this triangle here. So this is the hypotenuse, which is the weight. This is the x component prima, and this is the y component prime of the weight. So how much is this? Now, important, the y component is the adjacent of that. So, and the x component is going to be the opposite of that. This is the x component because this is x prime and this is y prime. So the x component, the x prime component of the weight, it's actually going in that direction, but it's the opposite of this angle. So SOHCA TOA, opposite is sine. So actually it's going to be the weight times cosine of 22. What about the adjacent? Well, the adjacent is this one, and that's actually COA, so SOHCA, excuse me. So SOHCA TOA, so cosine, this is the sine of 22 because it's the opposite. And the y component, as write it here, is going to be the weight modulus times the cosine of 22. So sine of 22 and cosine of 22, we can make the calculations. So first we realize that the weight, of course, is mg. That doesn't change, that's because of the Earth and pulling from the object. It's irrelevant which axis you choose. The force of the Earth on the object is the same. So what's that? Is the m times g, which is going to be mass is 7 times g, which is 10, so that's going to be 70 newtons. So oops, so that's the force, weight force. So now I'm going to have to multiply 70 newtons, so let's write, let's write the force of weight, which is going to be 70 newtons times sine of 22. Sine of 22 is 37, so that's going to be 7 times 37, and x component, and y component is going to be 70 times cosine, and the cosine is 0.92, right? And I'm happy, but I'm not, because I forgot something. What's that? X component, I go back and do sanity check, right? X component of weight is pointing in the positive x prime. But the y component, y prime component, is not pointing in the opposite, it's pointing in the downwards. So I have to add it a minus sign. So if I do that, then that's going to be 21, so probably 25, 26, right? And this is going to be 64, minus 64. Very good. So now I have my vectors. I can add them together. Let's erase this and finish this problem. So now we have that the normal force expressed in the x and y components are going to be 0 times f sub n modulus, and the y and the weight component, in the x and y, again the prime. If you want to add a prime in f sub n, that's up to you. Just remember you're describing that. That's about 26, and that's about minus 64. So when you add both forces together, of course, the total force, which is f sub n plus f sub weight, it's equal to 26 newtons in the x direction, and f sub n minus 64 in the y direction. And then I can do the same thing as I always do, which is say in x and y. So in the y component, in the x component, I'm going to have the 26, the force is equal to mass times acceleration in x. How much is the force? 26 newtons. How much is the mass? 7 kilograms. How much is the acceleration? That's what I'm trying to find. And this is, by the way, in the x primes, right? So this is in this direction, not this direction. It's this direction. It's sliding down and it's accelerating down. What about the y component? Well, the total force is going to be the mass times the acceleration in y in the y prime. And what is the force in y? Well, and what's the force in y prime? Well, that's going to be f sub n minus 64, equals to 7 kilograms, and then I sub y, which is what I'm trying to find. And then again, in x and y coordinates, in, y prime and x prime coordinates. Is the object moving in this direction? No, it's just sliding down. It's not a problem wording anyways, right? So it's not going upwards. So what's there going to be the velocity in this component? 0. Final velocity, 0. Change in velocity, 0. Acceleration, 0. Component y prime of the force, 0, because this is 0. Is not accelerating vertically. In the vertical now it means y prime, okay? So this is 0, so of course the normal force is 64 newtons. This is as we did before. But now we come back here and we're saying what's the x prime? That's going to be 26 divided by 7. So which is a little less than 4, so 3.7 meters square second. So if we want to see what's the acceleration, was 3.7 meters per square second. We can know this one even if we didn't know anything about the normal, right? It could be moving there. I mean, it's not going to be moving there. But it could be doing whatever. The force that accelerates the object down is in the direction of the slide, is not the normal. That's expected in this frame of reference, is the weight, with the weight component in the x. But there's also a weight component in the y prime, again. Why? Because otherwise there will be no normal force pointing in the y direction, right? And the object will be going this way. It will penetrate through the slide. So once we have the acceleration in x prime, we can solve the problem for x prime. And so we can go directly okay, so we can just write down the x prime motion, which of course it's x prime and x prime sub 0, v prime x prime that's unnecessary, and this is going to be b0x prime and ax prime and t. So the question is, if excuse me, if the object starts from rest at 12 meters up the plane from its base, what will be the block speed when it reaches the bottom of the incline? So actually this is not 12 meters height, this is 12 meters long, because it's saying here to here is 12 meters, and this is the initial position, right? This is the initial position. If you want, let's call it p sub 0, so we don't use x and y. So in the x prime component, we're going to do a delta x equal to 12 meters. That's given. So I could just decide that the initial position in x sub 0, which is going to be here, now I put the axis here then, right? So that's going to be y prime, and this is going to be x prime, right? A center here. So then x sub 0 is 0, and x is 12 meters, the 12 meters of the incline. What is the final velocity? I don't know that. What's the initial velocity? The initial velocity is 0. Why? Because it started at rest. What's the acceleration? It's 3.7 in the positive direction. And what is the time? We don't know that. So which one are being asked is x prime. We're missing t. Which equation do we use? V squared x prime is equal to Vx 0 x prime squared plus 2a sub x prime delta x. How much? We replace numbers. This is the velocity we're trying to find. It's equal to 0 squared plus 2 times 3.7 times 12 meters. So that's going to be 7.4 times 12, which is going to be 74 plus times 12, excuse me, times 12, and that's going to be 14.8, so that's going to be 88.80, look at that, 88.8, and that's going to be Vx squared prime, so the final velocity is just simply given as the square root of 88.8, which is equal to 9.4 meters per second. So that's the final velocity. So you see, we have completed the description of motion, and this is a beautiful example. I'm just telling you, this is going to cover 12 meters. What's going to be the velocity if it goes down this slide on Earth, which is another way of saying you the weight once they give you the mass, and what's the incline, which is a way of fixing what's the acceleration of this motion. So effectively, it's like if we were accelerating in this direction with the x component, x prime component of the acceleration in that, and for that we need to project. Again, you can repeat the entire problem and just solve it in here, but there's going to be a problem, again, which is going to be very uncomfortable once you reach that description to say, oh, you're moving 12 in the diagonal. If you want to say that, right, remember that this is 12, so your motion is going to need to be described maybe how in y, for instance, and you say how much is y, well, then it's going to be a matter of projecting, knowing the hypotenuse, and this is the opposite, so then you sine, you find how much is the height, and maybe you could calculate how long does it take, what's the velocity it reaches vertically, and then you would need to do the same thing with the horizontal, so that would be cosine times 12, cosine 22 times 12, and then you would measure what's the horizontal velocity on x, and then you take the square of one plus the square of the other, and the square root of that, that's going to be the velocity. It's going to give you exactly, it should give you the same thing, otherwise of course physics is a fraud, but it's not, it should give you the same thing, but it's going to be extremely much more elaborated. So this is one of those cases where frame of reference are independent, frame of reference are valid. Which one do I choose? The one that's more convenient to you, because at the end of the day, that the velocity is 9.4 meters per second, it's going to be the same regardless of how I rotate my axis. Velocity in modulus, right? So if you wish, it's going to be 9.4 meters per second in this one, in that one, in any other frame of reference that is stationary with respect to this frame of reference, which means it's not moving with respect to that. Let's do a few comments about problem 6. Problem 6 is an accelerometer, and that's a beautiful device because it's something that's going to allow you to experience and measure accelerations. And that's important because if you remember when we introduced frames of reference and also, Galilean relativity, we said that, well, the laws of physics are invariant in any inertial frame of reference, and we introduced that word inertial. Inertial means basically that there is no acceleration. So all of the systems are the same if they don't have acceleration. But as soon as you have acceleration, laws are going to be need to be adapted, right? And that's why further relativity theories came down the line. But the idea here is how can we determine if you actually have acceleration or not? It turns out that you cannot determine absolute motion in terms of velocity, but you certainly can determine acceleration. And how? Because masses have inertia. Masses are like, or objects have inertia, which they oppose. And as soon as they observe an acceleration, you're going to see the effects of that. Particular case in point, you have something like a pendulum hanging from your car, and then you accelerate, the pendulum goes back, right? And that angle is going to be the one that tells you, excuse me, how much acceleration so you have. So the question here is a small mass m hangs from a string and can swing like a pendulum. You attach it above the window of your car. When the car is at rest, the string hangs vertically. So if your car is zero velocity, this is the scenario. But as soon as your car and then the question is, what's the angle? When the acceleration it's 1.2 meters per square second. Now you can observe this yourself on your car. You sit on your car on a red light, and the pendulum is just hanging with your rear mirror. As soon as you accelerate, you're going to see that thing goes up. Does it really go up? No. What's happening is that the pendulum has what? Inertia, which means it opposes the change in motion. So your car is accelerating, but your object is not. It needs to impart that acceleration. And because the object is stationary, it wants to remain stationary. So you have the car and the object, the car accelerates. And because it's hanging with a string, the string is going to pull. And so you're going to see it goes backwards. So when you're accelerating forwards, it goes backwards. What happens when you're braking? The opposite. The object will go up. And that's what you experience as well yourself on the car, and that's why you should wear your seatbelt. Because when you brake, your inertia keeps going forward. You can go through the window. When you go reverse, if you start in your car and you push select reverse, and then you're going to go forward because your car goes backwards, but you stay there, right? So that's the idea. And with half a pendulum, meaning it's vibrating, it's going to go downwards when there's a positive acceleration. So based on this angle, we actually can figure out what is the angle. We can figure out the acceleration, or we can figure out from the acceleration what's going to be the angle, right? Typically you do the other way, and you have calibrated this so you can figure out what's the acceleration. So as always, we start with a free body diagram. What are the forces we're going to find? We're going to have a tension here, right? And this is the angle theta. And we're going to have a weight here, which is m times g, right? So we need to, again, split. We're going to use x and y coordinates as usual. This is x and this is y coordinates as usual. So what we're going to have to do is come with the tension and split it into the two components, right? So let's use the vector fashion. So we're going to need to find this one, and we're going to need to find this one, where this is t sub y, and this is tension x. Now this is theta, but we know this is the same we just did before. This is square, so this is 90 degrees. If this is theta, this is 90 minus theta. This is 90, so this means this is exactly theta. So then I can see again, let's rewrite this thing, excuse me, that this is going to be, this is going to be theta. And this is going to be weight, and this is tension. So how much is the force of tension? Well, the x component of tension is going to be given positive as the opposite, so that's so. So that's the sine of theta times tension, and the y component is going to be positive as well, which is f sub t modulus, and times cosine, because it's the adjacent of theta. And what about the weight? The weight is purely 0 in the horizontal component, and it's just purely negative m times g, with m being we're actually not given m, so we're just going to keep m equals to m. So that's just going to be minus m times 10, right? And so we need to add the forces together, so the total force is going to be sine of theta, we don't know how much is theta, in the x component, and f sub t cosine of theta minus m times 10 in the y component. And so the acceleration in the y component, now this is in your car, it's hanging from the mirror, and I ask you, your car is accelerating. What is the definition of the component of the acceleration? Is your car accelerating upwards? Well, no, your car is just moving horizontally. So what's going to be the change in velocity in the vertical? 0. The acceleration, therefore, 0. So acceleration of y is 0 physically. It's not accelerating up. Your car does not take off, right? But is it accelerating horizontally? Certainly, because the ball was kind of here, and because it went there, it kind of goes there, right? So that's acceleration, so ax is different from 0. So from here, immediately I'm going to see that this is equal to mass times ax, or let's write it down here, which is equal to mass times ax, ay. I know that this is 0, so the y component, which is this, is equal to mass times 10. And the x component, it's equal, which is the sine of theta, it's equal to mass a sub x. And we don't know how much is a sub x, right? But let's come here, and this is something nice of this math. What if I say, what is the direction of the acceleration? And actually, that's kind of what I'm trying to find in here. I'm trying to solve for theta, right? So let's say if I take x and divide by y, I have this. If I take x and divide by y, right, space, so I can take equation x, and I have ft sine of theta, ft cosine of theta. How much is this? This and this cancels. Sine of theta divided by cosine of theta, that's the tangent of theta. And that's equal to what? To x, divided by m times 10. And what happens here? This and this cancels. So I find that the tangent of theta is actually a sub x divided by 10. How much is a sub x? I was given 1.2 meters. Therefore, theta is the arctangent of that, and if I solve for that, that's actually 7 degrees. So then I have a formula, in this case, where I solve for theta. But you could use the formula the other way. The formula actually comes here. You don't have to know this. This is just a curiosity. The formula is, because you can derive it anyways, but you will not be asked to derive this in an exam, but the formula is that the tangent of theta, it's equal to a sub x divided by 10, and this 10, remember, is g. So this formula is a universal formula now. Every time I'm accelerating in the presence of a gravitational field, I'm going to be able to measure because of this g. And so if I was in the moon, the angle is going to be different because of the pull, but I'm still going to be able, once I know the g, I'm going to be able to know once I know g, I can figure out theta, or I can figure out ax. If I get theta, g times tangent theta is ax. If I know ax, divided by g, that gives me, g. And so I have here a way of finding relationship between the angle of inclination of the pendulum and the acceleration. In other words, acceleration is just simply g times the tangent of theta. If I measure how much my angle goes in the car, I can figure out how fast I am accelerating. If you push like a crazy the accelerator on a straight line with no pedestrians or anything, you're going to see the pendulum go super far away, very large theta. If you go slowly, you will see that the pendulum slightly moves. So that's something that you can observe. Your pendulum is your accelerometer. Then you know you're in a non-inertial frame of reference. Lots of physics have some issues in there.